Hello, and welcome to class 20 of this course. Today we're going to continue thinking a bit more about what our regressions mean. Okay, so in the last class, we talked about how well our regressions could predict things and how much we should care about how much they're predicting, and we talked about R squared and so on. Today we're going to talk about how much we should trust the models that we have. And the trust about our model is going to be divided between the issue of internal and external validity. In a nutshell, internal is going to be about the validity of the tools that you used and whether you should have confidence in what you found. External validity will be about how confident can you be that the results that you have, and provided that they are internally valid, can be extended, applied to other settings that are not necessarily in the sample that you use to estimate your regression. So let's start with a scenario. Imagine that at your future workplace, your colleague is asked to estimate the magnitude of a causal effect. So your colleague is going to first collect a random sample of data that she can use, and then she's going to use our knowledge of econometrics to run several regressions, because as we said in the last lecture, you may want to run more than one regression. You may want to make sure that your causal effect of interest is not sensitive to the inclusion of some control variables. So that's what we saw in the Nathan Nunn example, in which we would see several regressions, each one adding some more control variables, and seeing that the causal effect of interest, that is the effect in that case of the number of slaves in the past and the effect on GDP today, isn't changed by just including control variables. Once you have that, your colleague is then going to present the result. She's going to interpret the estimated coefficients the way we've been doing over and over in the lectures, and very often what was asked of you in the exams. And so she's going to say, I found these estimated coefficients. They are of this magnitude, of this sign, and they are statistically significant or not. After the presentation, your supervisor may ask you, do you think our results are valid? That is, say you kind of trust there's no omitted variable bias, and say you found something statistically significant. Does it mean that these results are valid? Well, that's not an easy question, or rather, the answer is not really easy. You cannot just say yes or no, because you need some criteria to decide whether you should say yes or no. So for instance, should you require that our estimated coefficients are exactly equal to the true effect in the population being studied? It means there is an effect of X on Y in the population. Remember that you did your estimation based on the sample out of this population. And so, should you say that the results that you get are valid if and only if the result that you get corresponds exactly to the population? Answer is no. And actually, very few studies really have the beta that corresponds exactly to what you would find in the population. And that's actually something we know. If you sample from the population, and that's something we discussed extensively at the beginning of this course, if you random from the population, depending on the sample that you're going to collect, you may oversample some parts of the population and undersample other parts. And so, on average, if you sample enough times your population, then you're going to be centered on the true value of beta. But in any given sample that you have, you're most likely than not going to have something that is a bit off compared to the population. Remember, that's also why we care so much about properties of OLS in large samples, because in large samples, we know we're going to get closer and closer to the true population. But there's another reason why you cannot say that your study is valid if the effect that you find is equal to the true effect in the population. And that reason is you don't know. Okay, you do not have access to the true effect in the population. If you had access to it, then the job is done. Okay, so you're only hoping that you have the right sample, that your sample is large enough and or representative enough that you're going to get something close to the true effect in the population being studied, but you don't really know what is the true value in the population. And so what you're going to require instead is that the statistical inferences that you're going to make about the effect of interest are valid for the population being studied. So you have a population, you're going to sample from it, and if it's valid for that population, that's going to be good enough. Again, this is not the population of the whole world, that's the population being studied. If you think back on the example from the first midterm, where we used the effect of the number of bedrooms on price of houses in Ottawa, well, your regressions are going to be valid in Ottawa. Okay, it may be that you can extend that to Montreal. It's probably not true in Toronto, where the housing market is so different. Okay, so you see already that things are changing depending on the context. Well, this thing about the context is going to be external validity. We're going to get there in a few slides now. But the internal validity is if you have results that are in line with what you would expect in the population being studied, then you have internal validity. Again, that does not mean you want the exact same number at what it would be in that population, because by the virtue of sampling, you're going to be off by some measurement. But if you have something that is trustworthy enough, then all you care about for internal validity is that it's representative of what's going on in the population being studied. Okay, so let's go into the details of what it means for our model to be internally valid. In large samples, you can do statistical inferences and say they are valid for the population being studied if the estimators are consistent and if the standard errors are consistent. Now, why do we need both? Well, we both need estimators and standard errors to be consistent because we're going to use both to calculate p-values and confidence interval. So I send you back to your lecture on this issue, but you remember that t-statistic that is used for the p-value depends on your beta hat estimated and depends on standard errors. So you need both of them to be consistent. Remember that consistent in principle means you want that the estimator and the standard errors are approaching the true values they would have in the population as your sample gets larger. Okay, in the case of the estimators, it's consistent if as n increases, as the sample size increases, the distribution of my estimator is centered around the true value of beta 1 and is shrinking around the true value of beta 1. We also want for these to be unbiased. So if you have consistency, you should have unbiasedness. But this is because if you have a small sample, then it would be nicer if your estimator is unbiased. You don't want to wait until you have a very large sample to actually be centered around the true value of beta in the population. So it would be nice if the properties of the estimator and standard errors are also true, unbiased in small samples. So we're going to refer to an estimator being biased if it is biased even in very large samples now. Okay, so that would be the case of an inconsistent estimator, but you should think of it as sample size increases, my estimate is biased, that is not on the true value, even if I increase my sample size. So when are standard errors biased? So I think biased, you know about the estimator. That's basically just being off by some measure. And that's something you know from, say, omitted variable bias. Okay, if you're in the presence of omitted variable bias, your beta hat estimated of interest is going to be biased. That is going to be off by some measure. And depending on the direction of the bias, you may have an upward or downward bias. So that's something you know for betas. That's something we never mentioned for standard errors. Well, actually, we mentioned them, but we never said these would introduce bias. If you have heteroscedasticity in your standard errors, in the error term, then you would have biased standard errors. Note that, as we said, a solution to that is to use heteroscedastic robust standard errors. Likewise, from our lecture on fixed effect models, if you have observations that are correlated, so that could be across time, across industries, you could use clustered standard errors so as to get rid of the bias. Okay, so you would have biased standard errors if you have either heteroscedasticity or if the IID assumption is not followed, but you have two solutions. In the presence of heteroscedasticity, you can use heteroscedastic robust standard errors. In the presence of non-IID data of correlated across observation error term, you can use clustered standard errors. So in both cases, this is solvable. So just because you know that in your data the error term is heteroscedastic doesn't mean necessarily that you're not going to get a valid model. You're going to have a valid, internally valid, provided that you use heteroscedastic robust standard errors. Say you know that the error term is not IID, that it's, say, autocorrelated, as we mentioned in a previous class, then you're going to use clustered standard error. Provided that you correct for those kinds of issues, then you will not have biased standard errors, and so you will have a valid model. In class, we mentioned one possible way by which OLS estimators may be biased, and that was omitted variable bias. That was the purpose of assignment 1. You spend a lot of time thinking about this, but you should know there are other ways by which the OLS estimators may be biased. And we're going to name 4 here. The first one is simultaneous causality. Of course, we're going to develop on that. But simultaneous causality means we always think about the effect of X on Y, but it may be that every now and then Y actually has an effect on X, and that they both alimент each other continuously. Okay, so we always have this arrow that goes from X to Y, pointing left, therefore, because we really want the causality of X on Y, and we really want that it is X that is changing Y, and not Y that is changing X. Then there may be measurement error. Sometimes you're going to measure things with some errors. That's going to be coming out of the data because, say, somebody entered the data by hand and humans are making mistakes. Well, if you have sufficiently measurement error, that may introduce a bias in your estimate. Sample selection may also be an issue. If that is, you don't really have a random sample if you have sample selection. If you want to look at some effect, but leave out some important part of the population of interest, then the result that you're going to find are not going to be extendable to the population you claim you're looking at. And finally, the functional form that you're going to use may be misspecified. We're going to see that in a bit. So let's go over another scenario. Imagine that you're an economic historian that is studying agricultural societies and that you notice that civil wars were very common in these societies. Again, you're an historian, you're looking at the past, and you're looking at societies where agriculture was the bulk of the economic activity there. A lot of people are working in agriculture. This is what defines these societies at the time. It turns out you may also see that these areas were also areas where civil war were very common. And so you may remember that a civil war is a war within a country or within some area under the same ruling where people are trying to take over power. So say that you also notice that this civil war tended to occur in years with bad crop yields. That is, every time you see that yields are bad, you notice that on the same year, a civil war occurred. Well, then you may want to test the hypothesis that crop yields were a cause of civil war. Again, you may think, okay, why do people are going to war, and in this case, civil war? Well, maybe a reason is every time the crop yields are bad, every time this is a bad year for yields, that gives people reasons to be angry, maybe, and to go to civil war. And say that you conduct this study and believe that you have adequately control for all reasonable omitted variable bias in your specifications. Now is an important distinction. Say you find a statistically significant relationship between the crop yields and civil war. That is, you know that the correlation between crop yields and civil war is statistically different from zero. Should you reject the hypothesis that crop yield did not cause civil wars? That's a slightly different question. The test that we've been using, the p-value that we've been using, are telling us whether there was a chance of observing such correlation by chance when there really is no correlation. The question we're trying to answer here is whether you should trust that crop yields caused a civil war. Okay, so irrespective of the effect that you're going to find, the magnitude of the effect that you're going to find, if you find something and that is actually statistically significant, so you know the correlation there is different from zero, should you still trust that you found the causal impact of crop yields on civil war? Well, here's an issue. One problem may be that you estimated a coefficient that instead captures the effect of civil war on crop yields. Note that I talked about correlation and having statistically significant correlation. Correlation, it doesn't matter which one is the dependent variable and which one is the independent variable. They are just correlated. But note that in a year where you have civil war, it may be that crop yields are really low. And this is quite obvious. In a year where you have civil war, well, maybe you don't have so many people working in the field, or maybe the war itself is destroying the fields. If it's the case, then maybe it is the case that civil war is causing crop yields to go down. The correlation goes in the same direction. Whether this correlation is significantly different from zero goes in the same direction. What is different? The direction of the causality. If you believe that crop yields make civil war more likely, but that civil war is making crop yields go down, then you're in the presence of what is called simultaneous causality. And that's another type of omitted variable bias that you cannot fully address just by controlling for things. Because if X has an effect on Y, but Y has an effect on X, well, you cannot control for X or you cannot control for Y because it's already there. So it's not enough for you to just use control to take care of this specific type of omitted variable bias. So let's check mathematically what this looks like. So here you have two equations, and let's assume they're both true. The first one represents the causal effect of X on Y, and this causal effect is captured by beta 1. And in this second equation here, we're looking at the causal effect of Y on X, and this is captured by gamma 1. Now, say for a given value of xi, ui, the error term, is large. Then this implies that for given value of x, if ui is large, then yi has to be large also. Now, take this yi and look at it here. If yi is large here, then xi has to be large. This means that you get a correlation between ui and xi. In other words, our main assumption that expectation of ui given xi is 0 is broken if it is true that you have these simultaneous equations together. So the beta 1 hat here, you hope you're capturing the effect of xi on yi, but you're also actually capturing the effect of yi on xi. This is what we're going to call the simultaneous equation bias. Let's go back to our civil war scenario and how this may impact the probability of crop failure. Think of factors that can probably cause civil war but are not directly a reason to be correlated with crop yields. Such example would be local lord had more than one son. So you have one lord ruling over some piece of land, and again, in this society, agriculture is the main source of revenue. If this lord has more than one son, then after his death, you expect that civil war is going to be more likely. That is, the sons are going to want to rule over all the land instead of just splitting it, and that would make civil war more likely. So here's the logic if you have such an omitted variable. If you have more than one son, civil war is more likely, and so crop yields would have also to be lower on average. When you have this, you would have to control for it, and whether the local lord has more than one son is going to be an omitted variable. Let's see another example of simultaneous equation bias. Remember from class 2, we looked at the Pascaline Dupas paper. In this paper, she's looking at how change in prices are going to affect the demand for bed nets. What was really nice about her setting was that because she randomly assigned prices, you know that expectation of ui given xi is 0. That's the beauty of running a randomized control experiment. If you think in terms of what has an effect on what, it's also nice because you only change x, prices, and looked at the effect on demand. You don't have something simultaneous here just because there was an intervention from outside. That's the purpose of this randomized control experiment. Now say that you have panel data in Canada about the quantity sold of wheat and the price. And say you want to run the log of quantity on the log of price. Now, by now you know that this would supposedly give you the price elasticity of demand. Now I'm asking you, if you do this, Do you have a model that is internally valid? Should you trust the result that you would get in this context where you would run the log of quantity on the log of price? So let me show you what this equation may look like, even though it's not in your slides. So define QIT as being the log of QIT and small PIT as being the log of price. Here's what Pascaline Dupin ran. She assigned prices and looked at quantity demanded. But again, she can do that, and she doesn't fear that expectation of UI given price is going to be different from 0 because she herself assigned randomly prices. Now, if you look at Canadian data, nobody changed prices. And specifically, if you observe, say that price is relatively low, then the quantity demanded should be relatively high. This means that beta 1 here is negative, okay? As price goes up, the quantity demanded goes down. And a bit like the same logic from the previous slide, check that if price goes up, then quantity goes down. But what happens to quantity and price in the second equation? I'll let you think through this, but this is the issue we're dealing with when we're looking at simultaneous equation bias. Let's now look at a new threat to internal validity of our model. And let's stick to our crops and war example. So imagine now that there is no simultaneous causality problem. Okay, so like we got rid of that somehow and we don't care about this anymore, or say it's just not a problem. Then imagine that historical crop yield is only as good as a random number generator. So again, crop yield is really just a random number. Then the true effect of a random number on incidence of civil war is 0. Again, if this is truly random, then the effect should be 0 because there should be no correlation whatsoever. So if you regress annual incidence of civil war on your crop yield variable, which again is now completely uncorrelated, then you should get a coefficient that should be close to 0. This is one way to think about classical measurement error. And so we can generalize this insight to the classical measurement error model. So let's define classical measurement error. Say your regressor of interest is xi, as usual, but you only measure or observe xi tilde. And so say that the regression that you care about is this one, the impact that x has on y, as usual, but that you only observe x tilde. Then if you regress y on x tilde, like so, what happens is you can substitute xi here in there. Okay, so take wi to the other side. You have a definition of xi, and take xi minus tilde and plug it here instead of xi, and you'll see that you will get this. Note that because you don't actually observe xi, then the difference between xi and x tilde, or just wi, again, take this one here and you'll see that wi is just x tilde minus xi, is going to be in the error term. This is again because you only observe x tilde, you do not observe xi, and so the part of xi minus x tilde you don't observe but actually has an impact on yi is now in the error term to some extent. We're going to talk about classical measurement error when wi, so that is here, has a mean of 0 and is independent from both xi and ui. Okay, so you have it here. In expectation, this is 0, so it's not correlated with x, and it's not correlated with the error term. So essentially, you added a random number to xi with expectation 0, and so on average, what you're adding to xi is just 0. So this is measurement error, but you're not adding some sort of bias in that sense. You're not adding values to xi in one direction or the other. But note though that when you're regressing y on x tilde, you're going to get a beta hat 1, which is no longer the beta hat 1 you're used to. And again, this is coming from the fact that beta hat 1 is a combination of x tilde and the effect on wi. And so actually beta 1 can be expressed as a ratio of the variance of x on the variance of x plus the variance of w. If this is a classical measurement error, then beta 1 hat is going to be biased towards 0. And specifically, the larger the variance of w, the smaller this whole term here, and so the smaller the beta hat 1 you're going to get. Don't forget, this is the true beta 1, but you're going to observe only x tilde. So the true beta 1 that you're going to hope to retrieve through the beta hat 1 is going to be biased by this expression here. So in the presence of classical measurement error, beta hat 1 is going to be biased towards 0. And again, you should think of it as the larger this term here, the smaller this part here, and it's going to go towards 0. What does it mean for the direction of the bias? Well, it all depends on what's the true value of the beta 1 of the effect of xi, not x tilde, xi, on y. If beta 1 is negative, then you will have an upward bias. That is, think of it this way. Say the beta 1 value in the population, the true one, is -5. But because of this bias, you find that it's 0 or even -1. Then you have an upward bias because it's not as small or as negative as it should be. Conversely, if the true beta 1 is positive, say it's 10, and you find that it's 2 because of this measurement error, then you're going to have a downward bias. Now, what would happen if we have measurement error in the dependent variable? Note that so far we've talked about xi measured with some error. What would happen if we have classical measurement error, but in the dependent variable? Well, again, say yi is measured with classical error. That is, what you would want to see, to observe, is yi, but by virtue of the data that you collected, or the people that collected the data for you, you only observe y tilde, and y tilde is a combination of the true value of yi plus some error. Again, you're going to regress xi on yi tilde, and what this means is that really, instead of regressing it on yi, you're going to have an error term that is going to add this error part here. And that's coming again from the fact that if you have yi on one side and y tilde minus wi, plug it here and take the wi over there. Okay, mathematically it's fairly easy. So now xi is measured with precision, but you have some error in the measurement of yi. Well, because it's a classical measurement error, and as long as the condition on xi are satisfied. So the condition that expectation of ui given xi is 0 has to be satisfied, okay? Just because you have measurement error, the other rules still apply. So you don't want omitted variable bias and the like, okay? But say it's satisfied. Then with wi in the independent of if wi is independent of xi, so expectation of wi given xi is also 0, then both together are also 0, and so beta 1 hat is going to remain unbiased and consistent. Here's the idea. As long as the measurement error in your dependent variable is unrelated to x. So say your x is the number of bedroom and y is the price of the house, like for the midterm one. As long as you're not making more errors in the price that you observe for houses that have, say, more bedrooms versus less bedrooms, then it's fine. You know, maybe you're collecting prices and you're not very precise, but as long as it's not correlated with your treatment, then the beta hat one that you're going to get is actually going to remain unbiased and consistent. There is a caveat though, and that's that because now your error term is a component of two elements, well, actually the variance of this whole term here is going to increase, and so does the variance of beta hat 1. What does it mean for inference? Well, as you know, if standard errors are larger, you're more likely to not reject the null hypothesis. You're more likely to say the effect of xi on y is not significant, and so you may falsely reject the null, not reject the null. You may falsely think that the effect of x on the true y is not significant when it is. Okay, so that's something to bear in mind. You may now wonder, what's a non-classical measurement error? Well, you're going to get a non-classical measurement error if your error, the measurement error, is actually correlated with your x. And then the direction of the bias for beta hat 1 will depend on this correlation. So think about our crop yield example. Say that for some reason you tend to have smaller values for the yields than they actually were at times of civil war and accurate otherwise. That is, you're going to measure yields with errors, and specifically in that case, you're going to underestimate the yields in times of civil war. But when times are good, you're going to just measure what it is. There are plenty of reasons to believe that that would be the case. For instance, maybe at times of war, people want to keep some yield for themselves for surviving to make sure they are never going to go starving. And so they may underreport the yields that they had in the year of civil war. So that's very plausible. If it's the case, then you're going to have a non-classical measurement error because your measure of yield is going to be correlated with the, like your error in the measurement of yield is going to be correlated with whether or not you have civil war. If you use this crop yield as a regressor, you would have a bias of the estimator of the effect of crop yield on civil war that is downward. Unlike with the classical measurement error, beta hat 1 may approach a negative number in large sample even if the true effect was 0. That's what we mean here by downward bias. Okay, so a non-classical measurement error of that type, that is a measurement error that is correlated with the effect that you care about. The measurement error is not just random, is not just coming from the fact that humans make mistakes, but it's actually coming from the fact that at times of war, you're more likely to under report yields, such non-classical measurement errors have to be taken into consideration very carefully. The bias due to either classical or non-classical measurement error are going to be called errors in variables bias. Okay, let's look now at another threat to internal validity of your model. And let's stick to our crops and war example. So you don't have to worry about measurement error anymore. You don't have to worry about simultaneous causality anymore. We're going to look at a new problem. And one that is kind of correlated with what I said about measurement error, but is not going to be measurement error. Say that the historical crop yield you have access to and the Civil War data actually have survived to the present day. But say also that for some reason that is clearly not random, in the years you have civil wars, you're less likely to have information on crop yield. Okay, so instead this would mean that your variable crop yield would have a dot, a missing value, specifically in the years you have civil war. This means that you are more likely to have missing observations for periods and locations that have more civil war conflict. If this is the case, then your data is going to be missing in a way that is related to the value of the dependent variable. And this can be a correlation between the error term and the regressor. The resulting bias is going to be called sample selection bias. And again, this is because you're going to effectively remove all the observations in which you have a lot of civil war because you don't have all the information for that year. We will not cover solution to sample selection bias in this course, but it's important to think about it. Up until now, we've always assumed that our data set was complete and that if some information was missing, well, basically it was random. You should think about sample selection bias as meaning that in some data set, some values are going to miss, and they are going to miss in a way that is correlated with the dependent variable. If it's the case, then this will introduce a bias, and your model is not going to be internally valid. Let's now discuss the last threat to internal validity of your model, and specifically functional form misspecification. Remember from class 13, we mentioned the possibility that the relationship between x and y could be nonlinear. We saw different versions by which this could be nonlinear, but let's think back on the quadratic form. So remember, we wanted to check that the relationship between quantity and price was indeed nonlinear. That was still with the Pascaline-Dupin example of bet nets. And so we checked whether price squared was going to be significant or not. If it was indeed significant, then it meant that the relationship between x and y was nonlinear. Again, if price squared was significant, then the relationship between price squared and quantity was actually nonlinear. That was also part of the question in midterm 2. So if it's the case, then it means that the true relationship between x and y is nonlinear. But still, economists really do like linear models. We know that linear models are just an approximation of the causal effect of interest, but there are reasons to prefer that to some other extent. So not everybody is going to look at this issue with a lot of concern, but note that if indeed the quadratic term is significant such that you have confidence that it's not linear. But this quadratic term is also as a potential omitted variable bias only on that squared term and not on the linear term, then, well, you would have an omitted variable bias. Thus, you couldn't very much trust your beta hat. This is all for all the types of threats to internal validity. As you may have noticed, we put more emphasis on the first two, but you should know about functional form misspecification and sample selection bias. Now, let's revisit what we mean by internal validity. You now know all the criteria that you would need to judge whether your colleague study, the one we mentioned at the beginning of this lecture, is internally valid. Note that you cannot make a definitive statement on the consistency of our estimators and standard errors. Instead, what you can do is make an educated guess about the sources of bias that are likely to be present in our study and what direction the bias might be. This means something I said several times, but I want to repeat here because it's very important. You can never prove that your model is internally valid. What you're going to do instead is try to list ways by which your model may violate the criteria we mentioned about internal validity. So in the model that you're going to see, you're going to wonder whether simultaneous causality may be an issue here. You're going to wonder whether functional form may be an issue here, whether sample bias may be an issue here, and so on. Okay, so internal validity is really telling you whether you did your job right, and you can never prove that you did your job right. You can just do the best you can, and usually this takes the form of a randomized control experiment. Remember that the very last recipient of the Nobel Prize in Economics, Duflo, Banerjee, and Kremer, are actually received that prize precisely because they are using randomized control experiment. Why do people like them so much? It's not just because when you have a randomized experiment, you don't fear about omitted variable bias either. You actually don't fear about any of the other threat to internal validity we mentioned today, okay? Because you have an experiment on which you actually have control over all the dimensions, then the internal validity of such experiment is actually very high. And that's what people really liked about this. But then there's a question of external validity. And that's a bit different. So external validity is about how much can you extend the results that you get from what you have, the context of your experiment or the context that you studied, to any other context. In the sample data drawn from a particular population, we're going to talk about the population study. So if you look at the relationship between bedrooms and prices in Ottawa, the population you studied are the houses in Ottawa. External validity is about, can I extend that the relationship between the number of bedrooms and prices is actually the same across all cities in Canada, all cities in North America, and possibly all cities in the world. This would be probably the population of interest. So again, say you have a randomized experiment in which you randomize the number of bedrooms and check the price in Ottawa. The population of interest is probably larger than Ottawa. Probably you're doing this experiment, but you want to know more about at least the market in Ontario, probably the market in Canada. if your inferences can be generalized to the whole population, to other setting, then you're going to say that you have external validity. In the case of randomized control experiment that the Nobel Prize winners were doing, a lot of the criticism they received was actually that external validity was quite poor. This is because usually the types of experiment they would do would consist in going to a single village or a few villages in a remote poor country in the world, run their experiment, have results that are extremely plausible, that are internally valid, but then when comes the time of extending that policy to the rest of the country or potentially whole poor countries in the world, then the external validity may not be as good. The external validity is therefore less likely if populations are very different across locations. So again, if you want to run a control experiment in a poor country, say, I don't know, the south of Morocco, well, maybe the results you're going to find are extendable to the rest of Morocco, but maybe they are not really applicable to I don't know, the South Asia countries, to say Vietnam. Maybe the context there is so different that even though you have a very valid internal model, your conclusions about the effect of X on Y cannot be extended to a different population. And that's what we mean by external validity. This completes class 20. 2 more to go.